All right, so let's start off with some derivatives of logarithms because I feel like that's the place we could probably use a little more practice. So let's say we had something like y equal to the natural log of cosine of x. We want to find the derivative. Well, so really at this point, kind of everything you look at, you should be thinking change. Like there's not going to be any just like straightforward e to the x, natural log of x. Like everything's going to be more complicated than this point. So I want to take the derivative of the natural log of cosine of x. I'm going to say, well, I know the derivative of the natural log of x is 1 over x. So the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And that's it. We can simplify this. We should simplify it. I wouldn't always say that, but this one specifically simplifies as just tangent, or I should say negative tangent of x. Which is kind of cool. Nice to see that that's the derivative of the natural log of cosine x. If we start getting more complicated, well, in fact, let's do one more before we get more complicated. If my function was f of x equal to the natural log of, say, x to the 4th plus 2, again, the derivative here, pretty straightforward process. 1 over the stuff times the derivative of the stuff, which I prefer to leave like this, but you could certainly write as one fraction like that. It doesn't really matter except for just trying to be more compact with our expressions. Now, things get more complicated, but not if we look at something like this. Say y equal to the natural log of, I don't know, x to the 5th times sine of x. You could certainly do this the hard way. You could right. In fact, I'm going to do it the hard way just to point out how you shouldn't do it. So here's how you could do it. You could say y prime is going to be 1 over the stuff. And then multiply by the derivative of the stuff. You have to use the product rule. It's going to be 5x to the 4th times sine of x plus x to the 5th times cosine of x. But you shouldn't do it that way. It's more work than you need to do because we can use our rules of logarithms to simplify something like this before we start taking the derivative. And that's kind of a general thing I should say is that if you can simplify something before differentiating it, it's often a good idea to do so. So what I want to do here first instead is to rewrite my function as y equal to the natural log of x to the 5th plus the natural log of sine of x. And then even go a step further and say y equals 5 times the natural log of x plus the natural log of sine of x. Then taking the derivative is much nicer. My derivative is going to be 5 times 1 over x plus 1 over sine of x times cosine of x, which is a much simpler process in my opinion. So typically, especially for logarithms, if you can expand it into many simpler logarithms, it's a good idea to do so.
So the problem with the simplification, both in logarithms and trigonometric functions, a lot of times you can simplify it before you take the derivative, but your answer is going to look very different.
It is, that's right.
Isn't that all problematic, like in the test?
Nope, it shouldn't be. Now, what I would say is, let me give you a worse example. Actually, let's before I give you a worse example, let's just make sure everyone's on the same page with the logarithm rules. So we have 3 properties of logs. Just make sure that everybody remembers them. Properties of logs are as follows. If you have log, doesn't matter what the base is, log base b of a product, you can break that up as log of the first thing plus log of the second thing. If you have log base b of a quotient, you can write that as log base b of the first thing minus log base b of the second thing. And thirdly, if you have log base b of a to some power, you can bring that power down in front of a logarithm. So those are the 3 properties of logarithms that we use to expand logarithmic expressions, make them larger and simpler before we differentiate them. So for those of you who came in here, where's the chat? Make sure you fill out the attendance form. For those of you that also here, make sure you fill out the attendance form by scanning one of the laminated QR codes there. All right, so let's look at something a little more terrible. Where'd you go? Sorry, got my papers all over the place here, which is typical. Yeah, all right, cool. So let's say we had something like I want to find the derivative of y equal to the natural log of x to the fourth times secant of x over e to the 6x times the square root of x to the third plus 9. Now here's what I'll say about this. You can see this on the test. I would totally ask this question on a test. And you can do it the hard way. You should not do it the hard way, right? Your teacher, someone will probably do it the long way, but you really, really shouldn't. You're making life way, way too hard for yourself, because if you do it the long way, you're without simplifying first, your derivative is going to be 1 over that stuff times the derivative of that entire mess on the inside, which is going to require quotient rule, product rule twice, chain rule a couple times. You don't want to do that. So the idea here is to make it really, really uncomfortable for you to do it the hard way. We want you to simplify this. We might not say those words in the problem, but if you see log of something gross, you should always think I'm supposed to simplify it first. So we're going to rewrite this as y equal to, now you can do this in as many or 3 steps as you want. I would probably do it in 2 steps. I'm going to show you 3. My first step would probably be this. To say it's the natural log of x to the fourth plus the natural log of secant of x minus the natural log of e to the 6x minus the natural log of x cubed plus 9 to the 1/2 power. Now, that's not maybe the first step you all would take, but I will tell you, when you see a logarithm of a thing, all the factors in the numerator end up with positive logarithms, and all the factors in the denominator end up with negative logarithms. The step that might precede that would be to say it's the natural log of the top minus the natural log of the bottom. And so then when you break up this, you get natural log of x to the fourth plus natural log of secant x. When you break up this, you get natural log of e to the 6x plus natural log of the square root of x equals 9. And then you have to distribute the minus sign to each of those pieces. So that's why they're both negative. Lastly, maybe not lastly, next to lastly, we bring down all the powers. So we still are just writing y equals because we haven't differentiated yet. So now I'm going to have y equals 4 natural log of x plus, there's nothing to bring down here. So I'm going to write this as natural log of secant of x. I suppose if you really, really wanted to, although I don't think you need to, you could write it as cosine of x to the negative 1 power and then bring down that, but that's not necessary. It's making life harder than we need to. Here I'm going to write minus 6x. I'm not going to write the natural log of e because natural log of e is just 1. And then here I'm going to write minus 1/2 natural log of x cubed plus 9. There's no way to break up the x cubed plus 9. That 3 can't come down as a power. We're stuck with it. Now we're finally at a place where we can differentiate, or we should differentiate. So y prime is going to be 4 times the derivative of the natural log of x is 1 over x. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff minus the derivative of 6x is 6. The derivative of 1/2 natural log of stuff is 1/2 times 1 over the stuff times the derivative of the stuff. And although we could do a little bit of simplification here, I don't really think that's super necessary at this point. The only simplification I will point out that is probably very typical to do is to cancel the secants there and just be left with tangent. And yeah, you could do something there too, but really, I mean, I would do it like this. You can ask a question if you have a question. I'm happy to address it.
Wait, so ln e6x turned into negative 6x? Is it ln e to what?
Right, the natural log of e is 1. So what I really have here is the natural log of e to the 6x is 6x times the natural log of e, but that's just 6x times 1.
Okay.
Yeah, that's why I have a 6x there. Other questions about this? So what about other bases? What if I had like the derivative of the log base 3 of x? Have we talked about this yet? I feel like we haven't. Okay. So the nice thing about logs of different bases is it's very, very easy to deal with them. There's a couple different ways to get there. The easiest way though is just to use the change of base formula. So so I should also point out, right? Change of base formula. Just says that if you have log base b of x, you can rewrite this using any base you want. So I can write this as log base A of X over log base A of B. And typically the base that we often use is the natural log of X over the natural log of B. You can use any base you want. One example I like to keep in mind, just because it's useful, is if someone asked you to say, find, I don't know, log base 4 of 8, you might just know what the answer is. Not too hard to do. But what's a base that 8 and 4 both have in common? 8 and 4 both powers of 2. So we can rewrite this as log base 2 of 8 over log base 2 of 4. Log base 2 of 8 is 3. Log base 2 of 4 is 2. And the answer is 3/2, because 4 to the 3/2 power is definitely equal to 8. So that's just an example of how the change of base formula is actually useful in other instances other than like trying to do what we're about to do here. Kind of cool. I mean, there are other ways to solve this. You could also solve log base 4 of 8 by setting it equal to x and rewriting it as 4 to the x equal to 8, and then 2 to the 2x equals 2 to the 3rd. So 2x equals 3, so x equals 3/2. That's another way of getting there that seems like a lot more work, but it's the same idea. Back to this. The whole thing we're going to do here is we're just going to say, well, instead of using this terrible base I don't love, I'm going to write this as the derivative of the base I want, natural log of x over natural log of 3. And then I'm going to rewrite it so I can see that as the derivative of a constant times my function. And we have constant multiples, and you take the derivative, they just get to hang out. So that 1 over natural log of 3 is just going to stick around, and you're getting it 1 over natural log of 3 times 1 over x. Or as people typically write, 1 over x natural log of 3. And this actually leads to a generalization. We can say that in general, the derivative of log base b of x is going to equal 1 over x natural log of b. You can go the long way or the short way when you do these. So for example, if I wanted to find the derivative of, say, log base 4 of x, you could either just say, I know the rule, and say it's going to be 1 over x natural log of 4, or you could rewrite it first. You could say it's going to be the derivative of the natural log of x over the natural log of 4. You really shouldn't, I shouldn't use it. You shouldn't use the quotient rule. It's definitely not a quotient rule kind of deal, because, well, actually, let me say that with another example. You shouldn't use the quotient rule here for the same reason that you shouldn't use the quotient rule to find the derivative of x to the 3rd divided by 4. You could use the quotient rule here, but you don't need to, because really you just have a constant times your function. And that's just going to equal the constant times the derivative of your function, which is 3x squared over 4. So when you have something that's a fraction, but your denominator is a constant, you can really just think of taking the derivative of the top and leaving the constant alone. And the work we're doing there is thinking of dividing by 4 is really multiplying by 1/4, and then that and that and that. But the shortcut is say, oh, derivative of x cubed is 3x squared. Leave the 4 on the bottom. Just like if I was taking the derivative of 6 times x cubed, I would leave the 6 out in front and get 6 times 3x squared, and then I would simplify. So if you're dividing by a constant, life is easy. Now, I will just point out, in case you're curious, you could use the quotient rule and it would work. I don't want to, but if you actually use the quotient rule for the derivative of x cubed over 4, here's what happens. You get the bottom times the derivative of the top, minus the top times the derivative of the bottom, all of the bottom squared. That's just 0. So you're going to end up with 4 times 3x squared over 4 squared. That 4 cancels with one of those 4s. And oh, look, we get what we should have gotten. So you can totally use the quotient rule here. You just don't want to because it's more work than you need to do. So back to this other one here. I can't ever keep, there's just too many papers. I have too much paper. That's the problem. I can't do it. Sorry. My problem, not your problem. So here, I'm just going to take the derivative of the top and get 1 over x over the natural log of 4. But I'm not going to leave it like that because I don't like fractions and fractions. So I'm going to write this as 1 over x natural log of 4. And it gets more complicated, right? You could say, I want to find the derivative of log base 7 of x cubed plus 5x plus 1. I don't want to do it the long way. I just want to remember the rule that if my base is something other than the natural base, I'm going to have to divide by the natural log of that base. So I know, and here's how I actually think of it. I just think of it as a log. Log, I don't care what base, I'll fix it in the end. I know when I take the derivative of the natural log or some log of a function, I get 1 over the stuff times, you guys know, times the derivative of the stuff, right? Change. So I know here I'm going to get 1 over the stuff times the derivative of the stuff. But then what else do I need? Right, I need a 1 over the natural log of my base. Now this looks kind of messy the way I've written it, so I would probably condense this down into one fraction where the numerator was 3x squared plus 5 and the denominator was x cubed plus 5x plus 1 parentheses natural log of 7. Just to make it look a little bit less cluttered. The idea is always the same. For a logarithm, your derivative is always 1 over the stuff times the stuff, and then if you have to, you divide by the natural log of your base at the end. Or if you prefer to say it, you multiply by 1 over the natural log of your base at the end. Kind of it. Is there anything else I want to say here? No, kind of cool. Yeah, so the base, so just like every time we talk about a different rule for differentiation, there's your kind of standard if it's a function of x version, and then you have the alternative chain rule version, which is going to be the derivative of log base b of some function of x is going to end up being 1 over your function of x times the derivative of your function of x times 1 over the natural log of b, or written in a less terrible way, f prime of x over f of x natural log of b. There's your chain rule version of the same derivative. The chain rule, but at this point, we should all be like, yeah, the chain rule version is always just what you'd expect it to be, right? You know, if you know a derivative rule, we know the chain rule version just by replacing x with a function, and then at the end, you have to multiply by the derivative of that function. Everything else kind of stays the same. Let's see. Yeah, cool. All right. So this also leads us to be able to then talk about derivatives of things like 4 to the x, where the base is a base other than e. So we know that the derivative of e to the x is certainly e to the x. We would like to find the derivative of 4 to the x. And there's a couple ways to do this. I'm going to show you 2 ways just because some people teach it differently and your teacher might do it differently. So here's the way I don't love, but the way that doesn't require implicit differentiation. So the second way we do this will require implicit. So we're going to rewrite this as the derivative of e to the natural log of 4 to the x. Come on in. You're good. Right, totally allowed. E to the natural log of some stuff is just the stuff. But then we're going to use our logarithm properties and say, oh yeah, that x can come down in front of the natural log. And so really we have got the derivative of e to the x times natural log of 4. Great. We know how to take the derivative of e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff, as typical. So the derivative of e to the x times natural log of 4 is going to be e to the x times natural log of 4 times the derivative of x times natural log of 4. I want you all to think about it for a second. We've got x times natural log of 4. I don't need the product rule because I have x times a. So the derivative of x times natural log of 4 should just be natural log of 4. I want you all to get real comfortable with the fact that natural log of 4 is a constant, right? Natural log of a number is just a number. I don't know what it is. Actually, I do know what it is. It's about 1.38 because I've done this 1,000 times, but like, it just happens to be a number I know. But the point is, natural log of 4 is just a number. It's never changing. It's always the same. So when you have x times natural log of 4, the derivative is just natural log of 4. Just like the derivative of x times 7 is just 7. Now, one last thing I want to do is I want to make this look nicer. Because no one wants you to write your answer like this. Because e to the x times natural log of 4 is the same as e to the natural log of 4 to the x, which is the same as 4 to the x. So really my answer should be written as 4 to the x times the natural log of 4. You might guess, we're going to see that the derivative of b to the x, where your base is something other than e, or even if it was e, is b to the x times the natural log of b. With the usual restrictions on our base that I didn't write down for this one or for the logarithms, the base should be positive, the base shouldn't be 1, the usual things we say about bases for exponentials and logs. Now there's in my opinion, a better way of doing this. Maybe not better, just I'm biased. That's also I'm biased. I'm biased towards doing it the other way, which is the following. So the other way to do this is to say we've got y equal to 4 to the x. And instead of doing what we did before, we're going to take the natural log of both sides, because that's often how we deal with a variable in an exponent, is by taking the natural log of both sides. And actually, there's a reason for doing this, because there's another type of function we're going to differentiate in like 10 minutes, where you kind of have to do it this way. You can't just do this other thing. So, well, actually, I take that back. You can probably do it either way, but whatever. It's good this way. So take the natural log of both sides. And then just like in the previous problem, we're going to bring that x down in front. So the natural log of y equals x times the natural log of 4. And then we're going to differentiate both sides. But here, we're not just making the assumption, it's actually very, very explicitly clear that y is a function of x. So when we differentiate the natural log of some stuff, we're going to get 1 over the stuff times the derivative of the stuff. On the other side, we talked about this just a minute ago, the derivative of x times a constant is 1 times the constant. And then we solve for y prime. So y prime equals y times the natural log of 4. But y is 4 to the x. So y prime is equal to 4 to the x times the natural log of 4. So either way, the derivative is 4 to the x times natural log of 4. It's great. Yeah.
So the base can't be 1 because that violates the base.
The base could be, well, the base could be 1. But if you try to graph like y with a log base 1 of x, in fact, we can talk about that for just a second because it's kind of funky. It's not that hard to figure out. If y equals log base 1 of x, what's the only thing you can take log base 1 of?
1
Volume. So x can be anything we want, but not really. What if x was 2? What's log base 1 of 2? Don't break your mind trying to figure it out because you can't. 1 to the what equals 2? There isn't a power that gets you from 1 to 2. So the problem with this is, actually, let's rewrite it. 1 to the y equals x. So no matter what y is, what's 1 to any power? So really, you're just graphing the vertical line x equals 1. So y equals log base 1 of x is not exciting. This is the same as just the graph of x equals 1. In a similar way, in fact, very similar way, it's exactly the same reason why 1 as a base isn't exciting if it's exponential. If you were to graph y equal to 1 to the x, that's just the horizontal line y equals 1. Also not particularly exciting. So it's not that they're not allowed, it's just that they don't really give us the thing we're actually talking about. This isn't really an exponential function, it's a constant function. This isn't really a logarithmic function, it's not a function, it's a vertical line that violates the vertical line test, but still not very interesting. So now that 1 isn't plausible, it's just not useful. Okay. Right, keep these in order. So let's continue on with this for just a second. Let's say I want to find the derivative of what have I got here? 5 to the x cubed. You can kind of go in either direction. And you know what? I should try to get over my bias. It's not, it's a perfectly valid way to do it the first way we did it. Sometimes it's nicer. Not everyone likes implicit. Although you should get over that because you're gonna have to use it even if you don't like it. But we can avoid it here. We can totally write this as the derivative of e to the natural log of 5 to the x cubed. And then we can bring the x cubed down in front and get the derivative of e to the x cubed times the natural log of 5. I do want to point out, just in general, you want to keep writing this ddx or whatever you're doing. Like all I'm doing right now is simplifying my expression. I haven't differentiated yet, so I should be careful. Or versus, you could also say, if you were going to write it as f of x equal to 5 to the x cubed, then you could write it as f of x equal to e to the natural log of 5 to the x cubed, and then you could write it as f of x equal to e to the x cubed times the natural log of 5. And then finally, at the next step, you'd be like, now I'm going to finally actually take the derivative. Or here, I'm actually going to finally do the thing and take the derivative and not write the derivative symbol anymore. But make sure you're writing the necessary symbols as you go along. Or the not, right, I'm not writing the derivative because I haven't done any differentiation. I've just done simplification. So here, the derivative e to the stuff is e to the stuff times the derivative of the stuff. Derivative of x cubed is 3x squared. Derivative of x cubed times the constant is 3x squared times the constant. And then I am going to rewrite it. E to the x cubed times natural log of 5 is 5 to the x cubed. So this part right here is just 5 to the x cubed. This is going to equal 5 to the x cubed times 3x squared times natural log of 5. Or what I would say more generally is if I just ignore the base like I did for the logarithm, I know the base, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So I know the derivative of some other base to the stuff is that base to the stuff times the derivative of the stuff, and I have to multiply by the natural log of that base. So we can make a more general rule and say that the derivative of some base to some stuff is that same base to that stuff times the natural log. Oops, I got out of order. I guess I should write the derivative of the stuff times f prime of x times the derivative of the stuff, then times the natural log of the base. I guess the order of multiplication doesn't really matter here, but I usually say it in my head one way, so that's the way I should write it. So for example, we don't have to do this kind of rewriting every time for this kind of thing. So you could say, if I wanted to find, I don't know, the derivative of 2 to the, I have to actually think of something, x to the 4th, plus 1. Instead of rewriting it as e to the natural log of 2 to the x to the 4th plus 1 and then bringing down the power and then taking the derivative, I'm just saying, okay, I've got the derivative of 2 to the stuff. That's going to be 2 to the stuff times the derivative of the stuff times the natural log of the base. That's it. It always works. It always works as long as your base is a constant. So I really need to pee. I drank too much coffee this morning. So I'm going to have you all to work on these next two problems. Find these two derivatives. Find the derivative of log base 4 of x to the 7th plus cotangent of x. And then after you've done that one, find the derivative of 3 to the, I'm gonna throw a product rule in there too, just to make it extra special. X cubed times cosine of x. 3 to the x to the, sure, that's fine. All right, you work on those, I'll go pee. Ready? Want another minute? More time? All right. Let's go ahead and go. So again, the idea here is that we are not going to rewrite these, even though we could. You could totally write this one as the natural log of x to the 7th plus cotangent x over the natural log of 4. And you can totally write this one as e to the natural log of 3 to the stuff, and then you bring down the stuff, and so e to the x cubed cosine of x times the natural log of 3. Those are things you could do for each of these, but we're not going to because we know the rule now. And really, here's what I'm thinking. I'm looking at these and I'm kind of pretending the base is just e. Really, that's what I'm doing. I'm looking at that and I'm seeing that's e to the stuff. I know it's not really e to the stuff, but I'm thinking about it because I know the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And then I'm actually saying, oh, but I really don't have e, I have 3. So at the end, I'm multiplying by the natural log of 3. Same deal here. I'm really thinking of this as the natural log of some stuff. I know the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And then I'm like, oh, but I really had a base 4. So I have to divide by the natural log of that base 4. That's really how I am actually thinking of it when I do this. So great. Derivative of, I'm actually really just saying log, and I'm pretending like there isn't a base to even say. Derivative of log of some stuff is 1 over the stuff. Okay, I can write cotangent times the derivative of the stuff. The derivative of cotangent is negative cosecant squared x, and then divide by the natural log of that base. And then probably rewrite it so it doesn't look like trash. So 7x to the 6th minus cosecant squared x over x to the 7th plus cotangent x natural log of 4. Same deal down here, or similar deal down here. The derivative of 3 to the stuff, or e to the stuff, is 3 to the stuff times the derivative of the stuff. I'm gonna have to use a product rule. I'm gonna come back for that. I mean, you could probably handle it, but I'm gonna come back for it. And then I need to multiply by the natural log of my base. And then I need to do one more thing because I actually have to do the product rule there. I can't just leave it like that. Derivative of x cubed is 3x squared times leave cosine x alone. I would write plus, but I know I'm going to be taking the derivative of cosine, so I'm going to think ahead and be like, oh, I don't want to write plus and then 3x cubed times negative sign. That feels terrible. I'm just going to write minus, and then you're going to have x cubed, and the derivative of cosine was the negative sine of x. They're not too terrible. Okay. So in the realm of kind of logarithmic things, exponential things, there's one last variety of things. So we have everyone's favorite e to the x or e to the stuff, and natural log of x or natural log of some stuff. Those are great. And then we've just kind of talked about how you could have a different base. And all that really does is make you end up multiplying by the natural log of the base if it's exponential, or dividing by the natural log of the base if it's logical. But then there's one other kind of weird situation which doesn't really, well, I was gonna say it doesn't really fall into either case, but you could sort of do what we did before. So let's say I want to find the derivative of x to the x. Now I'm going to tell you right now, we can't just say it's x to the x times the natural log of the base. That rule does not work if your base is not a constant. So when you have x to the x, or more generally a function to a function, you have to do the e to the natural log of x thing. Or really, I mean, that's not the way I would do it, but one way to do it is to do the e to the natural log thing. So let's do it that way first and talk about it. So I'm this is e to the natural log of x to the x, which again, we're going to use to bring down the power. So e to the, oops, I made a mistake. It's not a huge mistake. I can fix it. I said that the derivative of a thing was just the thing, but I still haven't taken the derivative. So I still need to write the symbol for I'm going to take the derivative later. And I'm going to take the derivative later. People do this different ways, right? You could also just write the function is, the function is, the function is, and then later on write f prime. That's probably how more people prefer to do it, I would guess, but I'm always trying to write the least amount of stuff possible. So writing the derivative of is easier than writing f of x equal to. Not a good reason, it's just the reason I have. So we're going to bring down that x and write x times natural log of x. Bless you. I assume bless you, but bless you anyway. You can bless you for a cough, it's totally fine. So just like before, we're gonna take the derivative of e to the stuff. The only difference between this one and like the ones we had before where the base was a constant was that now when we take the derivative of the exponent, we are gonna have to use the product rule kind of every time. Because you're gonna have that power that came down, which was a function of x, and the natural log of your base, which was also a function of x. So you're always gonna have a function of x and a function of x. So that's gonna end up being e to the stuff times the derivative of the stuff, which is going to be e to the stuff times product rule, 1 times natural log, 1 times natural log of x plus x times 1 over x, which we should simplify. Two things really. First of all, the e to the x natural log of x is just x to the x. So we're going to get x to the x. And then this might simplify a little bit. It does, right? X times 1 over x is just 1. So we should write this as x to the x times the natural log of x plus 1. And that is a perfectly fine way of doing it, but I do not like it. It's okay. I don't have to like it. The other way people attack this problem is by doing something where you do implicit differentiation. So let's look at a different example and see another way of doing this. So versus, let's say I wanted to find, let's see if I got some examples here. Do it. Why don't you? Yeah, I do. There we go. Versus something like finding the derivative of cosine of x, I'll say sine of x to the x squared power. So again, the intuition here, or the thing that I'm looking for to tell me that I need to do the thing I'm about to do, is the fact that I have an exponential thing, and both my base and my exponent have a variable. If that's the situation we see ourselves in, we either have to do this sort of thing up here, which I don't love, or we do the thing where we write y equals the thing we're trying to differentiate. And then we take the natural log of both sides. And the reason for that, again, is we're trying to do a thing that lets us get the exponent, the thing that's in the exponent out of the exponent, right? We don't want that exponent there. The thing we did here did the same thing, right? Writing this as e to the natural log of your stuff allows you to get that x out of the exponent there. So you're really just differentiating something that's a product and not some exponential thing. Yeah.
In this case, you can't move down.
You cannot. That is correct. You cannot move that down. So this is definitely not sine of x to the 2x power. I think is that what you're saying? Let me show you what I think you're saying, and then you can correct me if I'm wrong. I think you're saying we don't, and you're correct, we don't have this sine of x to the x squared, which you could write as sine of x to the 2x.
No, I'm saying, I thought you could move down that power to the front, like you would for a logarithm.
We could, once we take the logarithm. But at this juncture here, you're totally stuck. The x squared cannot come down until you have taken the logarithm of both sides. So if I take the natural log of both sides, I have the natural log of sine of x to the x squared power. Now that I have the natural log of this whole thing, oh yeah, this exponent can totally come down in front. But the only time we ever get to use that property is when you have the logarithm of something to a power. So we have to take the log of both sides before we can do that. Yeah, for trig functions, we have no analogous rule like that, unfortunately. So we have the natural log of y equal to x squared times the natural log of sine of x. And now we're in a situation where the right-hand side is something we are capable of differentiating. It's just going to be a product and a chain rule. So now we're going to differentiate both sides. The natural log of a function of x, the derivative is going to be 1 over that function of x times the derivative of that function of x. Chain rule. On the right-hand side, derivative of x squared is 2x. Leave the other piece alone. Plus, leave x squared alone. The derivative of the natural log of sine of x is 1 over sine of x times cosine of x. Finally, we do a bit of simplification. First things first, we want to isolate y prime. So multiply both sides by y. So we're gonna get y prime equal to y times all of this garbage, 2x natural log of sine of x. And they might write this as x squared times, let's see, cosine over sine is cotangent of x. And then finally, what you could have done in this step if you wanted to, is replace y with what it's equal to. Y is equal to sine of x to the x squared power. So y prime is going to equal sine of x to the x squared power times all that same stuff. Something you might have noticed after seeing a few of these exponential ones is every time you differentiate something that's exponential, whether it's e to the x or 2 to the x or x to the x or something to the something, that thing that you're differentiating always shows back up. So I want to kind of show you, right? Like when we differentiated 3 to the stuff, we got 3 to the stuff, and then some other stuff. When we differentiated 2 to the x to the fourth plus 1, we got 2 to the x to the fourth plus 1, some other stuff. So the thing that's exponential that you're differentiating always gets to still be there. It's always going to exactly show up as it was in your derivative. And then you'll have some other grossness after it, but that one piece will always be there for sure. So I'm not saying it has to be, I'm saying it is.
Why is that even important?
Well, because if I don't recognize that, I might not be careful about differentiating. So, right, when we use implicit differentiation, the idea is that whenever you're differentiating with respect to the variable x. And so what I'm really saying is I'm just using the chain rule here, right? Right here, I have the natural log of some stuff. And the derivative is 1 over the stuff times the derivative of the stuff. Whereas if I have the natural log of x, the derivative of the natural log of x is 1 over x. Because I'm differentiating with respect to the variable x.
So y has to be defined in terms of this.
Right, or we have to recognize that it is. So the thing here that I'm trying to help you avoid doing is saying the derivative of the natural log of y is 1 over y, end of story. Because it's not. It's 1 over y times the derivative of y because y is a function of x. Question? Well, what not natural log times something, natural log of something. Oh, like this here? Yeah, totally. So the whole, in fact, I would actually back up and say the reason that we are taking the natural log of both sides is to allow us to bring that power down so that we are able to differentiate both sides of the expression. That's kind of what's really going on here. So what I would like you all to try doing is this next one. So I want you all to try finding, it's gonna be similar but a little bit different. Try finding, so for y equal to, let's see, for a second, yeah, x to the sine of x power, I want you to find y prime or find dy dx. And you can do it either way, but no, you can do it either way. I would prefer you do it the second way we did it, but you can do whichever way you think you should do it. So either you're going to write the natural log of y equals the natural log of x to the sine of x and do some stuff, or you're going to write y equals e to the natural log of x to the sine of x and do some stuff. Well, I'll show you both ways when we do it, but I would do it. I like this. This is the James choice. I'll give you a couple minutes to work on that. So there is a general formula. I'm not gonna do it because it's not something you should try to memorize. It's gross to memorize. Like it's just not, the process is what you should memorize here.
But it does hold though.
You can find a general formula for the derivative of f(x). I mean, you should do it right now. Right, just write y equals f(x) to the g of x. Take the natural log of both sides. And follow the same process. Your answer should be something like x to the sine of x times sine of x times 1 over x plus the sine of x and natural log of x, something like that. I think. Yeah. You make sure of what they will say. Wait, your attendance difference around there. So I'm going to do it this way. So one thing I will say, and this is something that's important, to be able to do it this first way, where you take the natural log of both sides, you have to write it as y equal to your function. So if somebody gave you this problem and said, find, someone said, find the derivative of x to the sine of x, you can do it this way, but you have to write it as y equal to your function and then take the natural log of both sides. Or you cannot write it that way and do it this way without writing y equals, which is totally fine. Again, I'm always a fan of doing it this way because that's the way I've learned it and taught it for many, many years. I hadn't seen this other way of doing it until like maybe last year when someone taught it. I was like, oh, you can totally do it this other way, which feels wrong to me, but it's totally right. So it works. But here we're going to do this. So y equals x to the sine of x. The natural log of your function equals the natural log of your function. We took the natural log of both sides so that we could bring this power down. And that's just a general thing, right? If you see a variable in your exponent, regardless if you're differentiating or dealing, or maybe doing a limit later on with L'Hopital's rule, it is often a technique to be like, well, I don't like that. I'm going to take the natural log of both sides so I can not have a variable in my exponent. And then we're going to bring it down. We've got sine of x times the natural log of x. And now we differentiate both sides with respect to the variable x, meaning that the natural log of your stuff is 1 over your stuff times the your stuff. And really, you can think of that as implicit. You can think of it as a chain rule. They're really the same thing. Yeah. On the other side, product rule time. The derivative of sine of x is cosine of x. Leave the natural log of x alone. Plus derivative of, or leave the sine of x alone. Derivative of the natural log of x is 1 over x. I would probably encourage you all to not write things 1,000 times over and over. So I would, if I was going to solve this, I would do it in one more step. I'd say y prime equals y, which is x to the sine of x. Right, I'm multiplying both sides by y, and I'm replacing y with what it's actually equal to, times, and I would simplify this just a tiny bit. The only real simplification to do here is to write sine of x over x. That's our answer.
If I got it right, it's just x to the g times by f divided by f plus derivative of g times f.
Yeah, I feel like you should have a natural log of something in there.
It's not shown up a bit.
Right, okay, yeah. So you could, so yes, you could memorize the formula that the derivative of f to the g is f to the g times, I don't remember what it was, f times g times natural log of f plus g f divided by g or something. Right. You could try to memorize that. I don't recommend it. You certainly can, although here's what I say, you could probably memorize it, but on an exam, I don't think anyone's going to be like, oh, they just memorized this formula. They probably are still going to want you to show this one. So again, it's a formula you could memorize. I don't really recommend memorizing it just because there's only so much room in your brain. And there's other more important things to have to memorize later. So this process is definitely the more useful thing to know rather than that particular formula. But it is kind of fun that you can do that. Right, no one's going to say it, so I'll just have to say it. So I just want to point out, I'm glad no one said it. Good job. this is not equal to 1. I just want to remind you, right? Sine of x over x, the limit as x goes to 0, sine of x over x is 1. But sine of x over x on its own is just sine of x over x. So thank you for not asking me if it's equal to 1, but I still felt like I needed to point out it's not equal to 1. Okay. Yeah, that's kind of that. All right, let's see. Oh, I know what I wanted to ask you all. I hope the answer is no, but I should ask. Has anyone in their class talked about, inverse derivatives? Meaning like this terrible formula for the derivative of f inverse of x? Yeah. It is really confusing. I would 100% agree. It's very confusing. I still have trouble with it. So let me try and make it slightly less confusing. Now, here's what I would really say. The stuff we've just been talking about, where you kind of, it's not always the natural law, but where you kind of find the inverse function and take the derivative of that instead, it's kind of a similar-ish idea. But let's look at some concrete examples to try and make a little bit of sense of it. Some people kind of skip this completely when they teach this class, so I don't want to get too into the weeds with it, but we'll talk about it for a minute, and then we'll talk about some inverse trig, and then we'll talk about some related rates. Yeah, I think that's good. So let's look at the following example. Let's graph actually f of x equal to x cubed plus 1. And we'll also graph the inverse function in a second, but let's start with that. So x cubed plus 1, not my best thing to graph ever. It's usual. I'm going to graph it a little exaggerated so I can make it look not super terrible. So that's just my usual cubic function shifted up 1. So I've got the point 0, 1, I got the point 1, 2, I got the point 2, 8, which I'm not going to make super high up there. So it looks something like I blew it already. It doesn't look like that. I'm gonna try again. Sorry. I want it to look like normally I'd be like, it's fine, but this one actually needs to look pretty good so that we can see the things we need to see. So let me try this one more time. Blowing it. What I failed to do was I failed to write this graph should kind of level out when x is 0. It should flatten out because that's where you have like a critical point. So if I graph this slightly better, I'm going to have the point -1, 0, and I have the point 0, 1, and the point 1, 2. So it's going to look kind of like this. Cool. Yeah, that's decent enough. 0, 1, 1, 2, and the point I actually care about, 2, 9. All right. And now I'm going to also graph the inverse. Now let's find the inverse. So if inverse of x, which we'll graph in red here. So to find the inverse, we write y equals x cubed plus 1. And you can either switch x and y first or just solve for x either way. I'm more of a switch first person, but we'll do the other way. Y minus 1 equals x cubed. Y minus 1 cube root equals x. And then you can switch for x and y. So then we switch and we get y equal to the cube root x minus 1. So there's your inverse function. F inverse of x, f inverse x, we don't say of really. F inverse x is the cube root of x minus 1. Some functions are really easy to see what their inverse is because you're really just kind of undoing things in the opposite order. So for f of x equals x cubed plus 1, you're taking x, you're cubing it, you're adding 1. To do the inverse, you first subtract the 1. Take the cube root, just undid what you did. That's very basic level what an inverse does, is it undoes what the other function did. Some other functions are more challenging to do. You can't just talk it out like I just talked about, but some functions like this are pretty easy.
The way that our professor like writes it down is f to the negative.
Yeah, that's what I'm writing here, but I'm saying the correct words, which is
It says of y instead of x.
oh, that's a totally also valid way of doing it. You could, but the thing is, typically I'm graphing this still on the same XY coordinate system. So you're right, it's totally fine to say that f inverse of y is equal to the cube root of y minus 1. That is also valid. Where you're thinking of your input as y and your output is the cube root of y minus 1.
Oh.
I know, right? It's wonky. That's what you said, though, right? That's what they're doing. Yeah, it's totally fine to say that or that. You're still like in either case. I could input. I don't know. Let's say I could input 9 If I plug in 9 here, I get out 2. So I get the point 9 comma 2. Or if I plug in 9 here, I get the point 2. The point of writing it this way, I think, is to see that the things you're inputting here were the y's that you were getting from your other function here. That's, I think, why one would maybe choose to write it that way specifically. But give me 1 second. So I just want to point out that for f of x equal to x cubed plus 1, we've got this table. We can make a table of x's and y's. I'm just plot a few values there. X could be -2, -1, 0, 1, 2, and the y values would be -8 plus 1, -1 plus 1, 0 plus 1, 1 plus 1, 2, 8 plus 1. And then if I want to find the inverse function or plot the inverse function, f inverse of y, if you want to do it that way, even though it feels weird to me. My inputs, well, I'm thinking about inputting the y values here. So these are the inputs I want to get the corresponding outputs. So I'm going to input, like if I plug in -7, -7 minus 1 is -8, cube root of -8 is -2. And if I plug in -1, sorry, if I plug in 0, apologies, 0 minus 1 is -1, cube root of -1 is -1. We can see the interchange literally of the x and y coordinates, which is what you should get if you're literally interchanging x and y to get the inverse function. There's this very, very straightforward, it doesn't feel straightforward at first, but there's this very straightforward relationship between, oh, we're actually switching x and y, and on the graph, we're actually switching x and y, right? The x and y coordinates are just changing places. So instead of getting the point, say 0, 1, and 1, 2, and 2, 9, we're going to get the points 1, 0, and 2, 1, and 9, 2, which is what we exactly get, right? If you plug in 1 for your input, you get 0 for your output. If you plug in 2 for your input, you get 1 for your output. If you plug in 9, you get 2. And you could write this as, if you wanted to, although I don't love it, y f inverse of y. I'm not a huge fan, but it's totally fine. Okay, there were some questions.
What is a little confusing? Wouldn't that specific notation of that graph would be exactly the same graph? It would be the inverse graph, isn't it? Because y is still y.
Well, it depends on what you're saying y is.
Isn't y defined as the output?
No. If I look at this function I've written here, I am thinking of y as what I'm inputting, and then what I'm getting out is the f inverse of y.
So we could do the same exact process that you did over there, but instead of switching it on y, we just write a f.
Right. You could have totally stopped right here and said f inverse of y equals the cube root of y minus 1.
That would be not what we show, right?
Yes. Yeah. Now the idea is no matter which way you write it, whether you write it like this or like this or like this, the idea is your function is the cube root of blank minus 1, the cube root of your input minus 1. And so you should think of, I'm putting something in there, that's your x value, even if it says y, and you're getting out whatever's over there, and that's your resulting y value, even if it isn't what it says y is.
So y in this is not the y-axis value, it's the x-axis.
I mean, that's the way. It depends on what your professor wants you to do.
Because he solved it the same way,
Right.
but the notation is just weird.
Sure. So let's hold off on this particular topic for just a moment, because I think I understand what your professor is trying to do. They're trying to get you to the formula part where you do the derivative of the inverse, which is where we're working towards. We'll circle back around to that. But let's hold off for a second. So I'm going to graph the inverse function here. Cube root of x minus 1 literally is going to look like what happens if you just reflect the graph across the line y equals x. So here's good old y equals x. All I'm doing is reflecting all these points across that line. So instead of 0, 1, I get 1, 0. Instead of 1, 2, I get 2, 1. Instead of 2, 9, I get 9, 2. And then instead of 0, 1, instead of -1, 0, I get 0, -1. I get some points over here as well. So it kind of looks like that. Okay. And this is my inverse function, f inverse of x. My original function, f of x. So here's what I want to actually talk about. How does the slope of your original function f of x when x is equal to 2 compare to the slope of f inverse of x when x is equal to 9? Let's just find them. So here's what, and this is actually, this is kind of the super important part. So f prime of x is easy. It's the derivative of x cubed is 3x squared. And if we plug in 2, f prime of 2 is equal to 3 times 4, which is 12. Great. Okay, now let's answer the second question, which is a little more work, but not too much. So our inverse function was, again, this cube root of x minus 1, or as I would probably write, x minus 1 to the 1/3, just to make it easier to differentiate. And now I'm not going to write f inverse of x prime because it's annoying notation. I'm going to use what's kind of typical for this, which is to write it as the derivative of f inverse dx. And I know I should have found the derivative first. Oh, no, I'm sorry. Brain. So the derivative here is going to be 1/3 times x minus 1 to the negative 2/3. Times 1 if you want to think about the change, right? Times the derivative inside stuff, but no big deal. Okay, so now if I plug in, I'm not going to write df inverse dx parentheses of 9. I'm going to write evaluated at x equal to 9. Or professor might say at y equal to 9. But now if we do this, look what happens. We get 1/3 times 9 minus 1 to the negative 2/3. 8 to the 2/3 power. Well, 8 to the 1/3 is 2. Cube root of 8. 2 squared is 4. 4 to the negative 1 is 1/4. Just hold on just a minute. We're about to see why, I promise. This is 1/3 times, let's see, 8 to the negative 2/3 was 1/4, which is equal to 1/12. And here's the thing you want to see. These derivatives are reciprocals of each other. This is not a coincidence. This is what happens all the time. So these are reciprocals. Look at the graph. The slope here is super duper steep. And the slope over here of this interchange graph at this corresponding point is exactly as shallow as the other one is steep. This one is a rise over run of 12/1, right? Over 1 up 12. And this one's doing the exact opposite thing because the x and y things have switched. And so this one's going over 12 up 1 instead of over 1 up 12. And that is the nature of this relationship between these two functions. To find the derivative of the inverse at some point, you find the reciprocal of the derivative of the original function at the corresponding point. That's why you have to do this whole weird thing where you switch the input to being the output of the other thing. Like it feels very backwards a lot of the time. But this is really the idea, is that so the way I would write this, and again, I will be perfectly frank, this also is challenging for me. I often have to really think about how I'm writing it the right way. So let me see if I can write this the right way for you all. Ooh, right here. So here's here's the general kind of idea. Here's our theorem. Oh, this pen is trash. Keep trying to make this pen work. So here's a theorem. It's like the inverse derivative theorem. I'm just going to say it's the theorem about the slope of the inverse function, or of an inverse function. So I'm going to throw away some pens. I don't want to, but I should. So here's the idea. The derivative of f inverse evaluated at some point B is going to equal 1 over the derivative of the original function evaluated at not B, but the corresponding place on the other function. So it's going to be f inverse of B. So let's look. So I know this seems kind of wacky, but let's actually look back at our previous example. So let's say again, our previous example, our f of x was, what was it? It was x cubed plus 1. We're not even going to write down the inverse. And the place we were trying to find the derivative of f inverse at, let's see, we found the derivative of f inverse at x equals 9. So that's what we were trying to do. We're kind of retrofitting what we did before to make it work. But that's seriously, let's pretend like they said, okay, James, here's your function. I'm not going to tell you what the inverse is. Find the derivative of the inverse at x equals 9. Or maybe b equals 9 is a better way, right? Because writing x, I feel like it's confusing. So here's how it's going to work. It's going to be 1 over the derivative of f evaluated at f inverse of 9. What the heck is f inverse of 9? Well, you don't usually have to know the inverse function to figure that out. Because f inverse of 9, there's this whole relationship between f of blank equals 9 is the same as f inverse of 9 equaling blank. So if I look at my original function, can you all think of a number I could plug in for x? I know it's literally on the graph. If I plugged it in for x, I would get an output of 9. 2. So f of 2 being 9 is equivalent to f inverse of 9 equaling 2. All we're doing with this is saying, oh, instead of actually looking at this point on the inverse function, I'm going to look at the corresponding point on the original function, find the slope there, and then take the reciprocal of it. That's what we're doing. That's exactly what we're going to get here. So we're going to get 1 over f prime of, well, f inverse of 9 was 2. And that's going to be 1 over, well, f prime is 3x squared. So it's going to be 3 times 2 squared, which is 1/12. It's not my favorite formula, as you might have guessed by the way I'm talking about it very aggressively, but it has its place. Now, the thing is, a lot of the time, you don't need this formula. Some of the times you do. Some people are good at making up problems that require you to use this formula. But most of the time, if you have a function that you actually just want to differentiate, we have other methods of getting there. So to work back around to the whole XY issue from before, the reason why your professor might be using Y is to kind of emphasize the fact that the thing you're plugging in here is actually the Y value of the other function. Right. So if I'm trying to differentiate this inverse function at the Y equal to 9 value, right? The 9 value is the X value for that function, but it's the Y value for the thing we're actually going to differentiate. So that's possibly why they're using that. I can't say 100% for sure, but it's likely.
You're performing the operation of the inverse on the output of the original function. You want to repeat that?
We're doing the operation of the inverse on the output of the yeah.
Is that
Yeah.
Is that
Yep. Yeah. So then you can kind of move away from the picture and ask kind of stupid questions like, what if sorry, I should point out there's other notation for this, just so everyone can see it before we go on here. The other way people often write this is as the derivative of f inverse with respect to x evaluated at x equal to b is 1 over the derivative of f with respect to x evaluated at x equal to the inverse of b. to me, the hard part for this is always figuring out what the heck I'm plugging in. Like finding the derivative of the function and then dividing by that, no big deal. But figuring out what number you're actually plugging into that inverse is always a little bit confusing, I feel like. So let's look at one example, maybe two examples, and then we'll move along. So find the slope of the line tangent to the inverse of f of x equal to x to the fifth plus x cubed plus x at 3, 1. Now, the point of this question is to make it so you cannot actually find the inverse function. This function is invertible, and I know it's invertible because I know it's increasing. Right? It's this function, right? As x gets bigger from left to right, the outputs get bigger from left to right. You could also take the derivative, and take the derivative is 5x to the fourth plus 3x squared plus 1, which is always positive, and if the derivative is positive, that means the function is increasing, which I don't think is something we've actually talked about yet, but it's something that's true. The derivative is positive, the function is increasing. The derivative is negative, the function is decreasing. So this function is definitely always increasing, and any function that's always increasing or always decreasing is invertible. So it's 1 to 1. So this is invertible. I want to find the derivative of the inverse, or the slope of the tangent line of the inverse function at the point 3, 1. So the question we have to ask ourselves is, okay, great. I know I want to find, sure, f inverse of, I'm not even sure, I got to be honest. So f inverse prime of some point equal to 1 over f prime of f inverse of that same thing. What's that? I gotta be honest, I'm not gonna lie, I have a hard time thinking about what it is. You might be right. I can't answer that question because I have to think about it before I can answer that question. So here's the thing I want to point out. Is the point 3, 1 on this graph? Yes, we do. If you plug in 3 for x, what do you get for y?
1. 3, 1, right?
All right, but so let's read the question again very carefully.
Okay.
Find the slope of the line tangent to the inverse of this function at the point 3, 1. So this point 3, 1 is on the inverse. So maybe they wrote it poorly. Sorry, they was me. Right, so the point 3, 1 is definitely not on that graph. The point 1, 3 is on that graph. If x is 1, you definitely get f of 1 equal to 3. So this thing definitely has the point 1, 3. This thing definitely has the point 3, 1. So I'm trying to find the slope of the tangent line. And again, we can draw pictures here, right? Just to kind of to make more sense of this. Here's what we're saying. We're saying, okay, well, I've got some function. Maybe it looks like that. And here's the point 1, 3. That's my original function. And then here's my inverse, which I'll try and draw looking somewhat inverted. And I'm interested in what's happening at my inverse at the point 3, 1. So I want to find the slope of this line here, which means I'm going to find the inverse of the slope of this line here. So I want to find 1 over f prime at that point there, which means it's going to be f inverse of 3. It takes some mental gymnastics. I mean, clearly I'm having a hard time with it, right? It's something that I've always, and you know, some people are better at something than others. This is probably something that I've always struggled with because I've never fully taken the time to really make super sense to me because it's just not that important to me, to be honest. It should be maybe, like, I should probably get better at it. But the idea here is that, okay, great. We're trying to find the slope of the tangent line here. So we're going to find the slope of the tangent line here at f inverse of 3, which is 1. Right? F inverse of 3 is 1. If you plug in 3, you get back 1, or f of 1 is equal to 3. Those are the same thing. F of 1 equals 3. F inverse of 3 equals 1. So what we're really doing here is we're saying, okay, that's going to be 1 over f prime So that's going to be, I never liked this notation. F prime of x is 5x to the fourth plus 3x squared plus 1. So we're going to plug in 1 to that and get 5 times 1 to the fourth plus 3 times 1 squared plus 1, which is going to be 1 over 5 plus 3 plus 1. That's kind of it. Now, I feel like I might have accidentally made this problem. I know it doesn't feel this way, but I might have made it too easy. We'll look at one more and we'll make it a tiny bit harder. Okay. So let's do one more. Do I have one more? No, I can make it. Oh no, I do have one more. Cool. So let's say I want, yeah, all right, cool. So I want to find the derivative of the inverse function at x equal to 1 for the given function f of x equal to e to the negative x squared plus x. Okay. So we kind of know what to do. We know we're supposed to find the derivative of this function and then divide by it. The point is to figure out where we have to plug in. But let's find the derivative first because we know we need to do that. So our f prime is, okay, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Derivative of x is 1. Now, good bet that we're not plugging in 1. Again, graphically, what we're thinking is maybe here's our inverse here. I mean, I've just drawn this, right? Here's our function. Here's our inverse. Maybe here's the point 1 comma whatever. If I want to find the slope of the tangent line here, what I'm really doing is finding the slope of the tangent line here and inverting it. So I don't want to actually plug in 1. I want to plug in whatever is giving me 1 there. So let me ask you all, what do I need to plug in for x so that f of that is equal to 1? Now here's the nice thing. It's usually meant to be something you can easily guess. So there's not a lot of things you can plug in and say e to the something of them is going to be a nice number. What's kind of the only thing you can plug in for e to the something and get a nice result? Right. So 0 is what we should guess. And oh, look, f of 0 is e to the 0 plus 0, which is 1, which is what we wanted. So usually it's the most likely candidate. If they give you a problem like this, the thing you're looking for is, well, okay, if I plug in 0, it's going to work. There's not a lot of choices. So the idea here is that that's going to be 0, and that's what we're going to plug in. So df inverse dx at x equals 1, the derivative of f inverse evaluated at x equals 1 is going to be the same as 1 over the derivative of your function evaluated at x equal to f inverse of 1, which is also known as x equal to 0. And so then we just go along our merry way and say, okay, great, it's going to be 1 over this derivative, e to the negative x squared times negative 2x plus 1, evaluated at x equal to 0, which is not very exciting. It's going to be 1 over e to the 0 times 0 plus 1, which is just 1. But that's the idea. Like, so to me, I feel like the hard part of this problem is not finding the derivative of whatever. That's fine. It's figuring out what you're supposed to plug in. And the thing you're supposed to plug in is the f inverse of what you're trying. So if you're trying to find the derivative of f inverse at some point, the actual thing you have to plug in is the inverse function of that point. Okay. Oh, good. I'm glad. Sorry, I didn't see the chat, but yes, I'm glad that makes sense. Assuming that's what. Oh, well, that was a while ago. Maybe you weren't talking about this. I'm glad something made sense. I might have worded it somewhat poorly. I suppose I was going to, if I was going to say, I would say I want to find the derivative, find the slope of the tangent line of the inverse function at x equals 3. So a better way to have written this would have been to say, sure. So I could have written this as Find the slope of f inverse of x at the point 3, 1 for the function f of x equal to, or given maybe, given that the original function is x to the 5th plus x cubed plus x.
And we will know that when it's on f prime, f to the power.
F inverse of x, yeah, I would agree that the wording I wrote in the original one, it was not made super clear which function 3, 1 belonged to.
So f inverse on f can never collide either, right?
So one more time.
F inverse on f can never intersect.
Oh, they definitely can intersect.
So what if the point is on both graphs?
So if the point was on both graphs, I mean, the x and y coordinate would have to be the same,
So it would just be 1 over the 2 with the constant.
right? Because if the graphs intersect, which is totally possible, right? Like for example, x cubed and well, that's not x cubed and x to the 1/3. Those are totally inverse functions, and they intersect in like 3 different places at the origin at 1, 1, and at -1, -1. That would be kind of great because then no matter which point they give you, if they give you the x or the y, they're the same as each other, so you're kind of set.
It's just 1 over the root of whatever.
Right, yeah. But then the point you're plugging in, if it's one of those points that intersect as well, no matter which one you're thinking of, it's the same value because it has to be.
Sure.
Right. So yeah, so inverse functions, if they do intersect, they only intersect at points on the line y equals x. Because you have that symmetry. All right, I think that's enough about those. Feel like we should, there's so many things to say. So should we talk about related rates a bit? Like maybe related rates? Yes, I think so. Let's talk about some related rates, at least a couple of examples. So you're all going to see related rates. So if you haven't seen it yet, I'm not wasting your time. Related rates are definitely coming up for sure. No, you have to, even if your teacher never talks about related rates, you should still learn about related rates. Like it's something you should see because it's an important topic in calculus. So if I can find my examples. I mean, I can think it up. Yeah. Let's just start off with the classic example. So you throw a rock in a pond. Because you know it's fun. Throw a rock into a pond and circular ripples form. Expanding at a rate of, I kind of wrote that carefully, of the radius increasing. Sorry, it's too many words there. Apologies. The radius of these circles increase at, let's say, 3 feet per second. That's too many words for saying that, but oh well. So you threw a rock in a pond, circle's getting bigger, and the circle is getting bigger in a way that the radius is increasing at 3 feet per second every second until they get too big and they disappear. The question is, how fast is the area of one of these circles increasing? Maybe, I don't know, 5 seconds after throwing the rock in. And so this is why yeah, we can definitely talk about inverse trig next class. Yeah. This is why, and we did talk about it a little bit last week, just a tiny little bit. This is why it's called related rates, because you're given one rate, in this case, the rate of how the radius is increasing, and you're asked about a different rate, the rate at which the area is increasing. So hence the name related rates. And like many of the things we've seen, it's all going to really boil down to just chain rule / implicit differentiation, which are kind of the same thing. So let's write some equations. We've got, or we can draw a picture, I suppose. Pictures are nice. I feel like for a circle that's getting bigger, you don't really need a picture, but you could draw one. So the idea is we've got the radius, and the radius is increasing, so it's moving outwards. And we're kind of going to get bigger, and so we're going to get a new circle that's even bigger. So typically when you're dealing with a related rates problem, you want to find an equation relating the things that are changing. So I'm going to say, okay, well, we know an equation for the area of the circle. Area is equal to pi times r squared. Usual area of a circle kind of deal. Now, here's where things are going to get interesting. We're going to differentiate both sides. But almost always, although not always, there's some problems we'll make up that don't have a time component to them. But most of the time, you're saying something is changing as time goes on, right? The radius of these ripples are getting larger and larger and larger as time passes, right? It's not just happening magically, something else has to be changing. So typically, most of these related rates problems are something is changing as time goes on. Although there are some examples that do something slightly different, which is fine. So here the idea is we're going to differentiate both sides. Now, I've done this, no, it's fine. So we differentiate both sides and we say, well, the derivative of area is the rate of change of the area, dA dt. Because that's what we're interested in. We want to know how fast is the area increasing as time goes on. On the other side of things, we're going to differentiate that as well. What's the derivative of r squared? Right, exactly. So it's not just 2r, it's 2r times dr dt. Because the idea is that we're not differentiating with respect to r, just like way back when you differentiate like y squared, we're not differentiating with respect to y. When you differentiate y squared, like implicit, your y squared is 2y times y prime. Here, if you're differentiating r squared with respect to t, you're going to get pi times 2r times dr dt. Now, there's a way to make this look a little bit more sensible, although we typically don't because it's annoying. We could have said, well, really, James, you're kind of leaving out something important. You're leaving out the fact that both area and radius are functions of time. So you could be more explicit with your notation and say, well, really, you have a of t equal to pi times r of t squared. And then when we differentiate both sides, it's a little more obvious that, oh yeah, on the left-hand side, you're going to get a prime of t. And the right-hand side, you're going to get pi times a function squared's derivative is 2 times that function to the first times the derivative of that function. And now it's maybe a little more, that's a little hard to see is what it is. Maybe now it's a little more obvious that, oh yeah, we're just getting dA dt equal to pi times 2 times r times dr dt. We just like to write it this way. And then after that, after you differentiate both sides, the rest of the process is kind of a plug in what you know, solve for what you don't. So let's see. I know that I want to find how fast the area is increasing, so I probably cannot solve or plug in for that. So I'm going to have dA dt equal to pi times 2 times, I should be able to plug in for the radius. And so I have to do a little bit of exploration here. They asked me, how fast is the area of the circle increasing 5 seconds after throwing in the rock? So if I threw in the rock, 5 seconds later, well, if the radius is increasing at 3 feet per second, how big is the radius now? Right, it's 15 feet. Normally I wouldn't write the units, but I'm gonna write the units here. And then dr dt is how fast the radius is increasing, which is 3 feet per second. And then we can multiply it all out. Oh, question. Yes. So normally, actually a lot. So I would say a lot of the time they would phrase the question is how fast is the area of the circle increasing when the radius is 15 feet? I tried to make it a little trickier. I said I'm going to say how fast is the radius increasing, or what is the radius? I said how fast is the area increasing? 5 seconds after I threw it in. So I threw the rock in, plopped in. The radius increased at 3 feet per second for how many seconds? Right. So every second it got 3 feet bigger. So 5 times 3 gave us 15. Sometimes people will do that. We'll say how much time has elapsed and expect you to find the values using that. Sometimes they'll just tell you the values. Most of them will tell you the values.
So this is a specific problem, we know that radius starts at 0, is it always the case? Can we have initial radius that you have to add?
Right. So I would say you should assume that it's what we think it is, unless they've made it clear that it's not. So it's a safe assumption to be like, yeah, the radius is starting at 0. They're not trying to be extra tricky here, but you're right. Someone could give you a different situation for sure. So here we do this, we get pi times 2 times 15, which is 35 times 3. So we're going to get 90 pi feet squared per second. So at that moment, when the radius is 15 feet, or preferably after 5 seconds have elapsed, the area is increasing at 90 pi square feet per second. Now, what I want to point out is that if we had a different value, say we let it go for 10 seconds instead of 5 seconds. So this is for after 5 seconds. But if we let it go for 10 seconds instead, the area would be increasing at pi times 2 times 2 times, well, instead of, oh, sorry, the 2 is already there. Instead of 15 feet, the radius would be 30 feet times still 3 feet per second. That's going to double that and end up getting 180 pi feet squared per second. So it makes some sense if you think about it. The larger the circle is, if the radius is increasing at the same amount every second, you're going to get more increase every second because you're adding on this outer edge that's going to be a much more area than this small inner like circle. So that's why the rates aren't going to be right. That's why the area is increasing at an ever increasing rate, because they are not linearly related to each other, right? If for every increase in radius, your area is increasing by some square factor of that. Let's look at another example, because I want to walk a little bit more through how the general sort of process for doing this is. So let's look at something like, yeah. Sure. So we are blowing up a balloon, a spherical balloon. And we've got one of those like air tanks, and we are increasing the volume. We're blowing it up with air, increasing the volume at a rate of, say, 10 cubic centimeters per second. No idea if that's a reasonable rate. It does not matter. The question I want to ask is, how fast is the radius of the balloon changing when the radius is 6 centimeters? 6 centimeters. I can read it again for sure. So it says, so we're blowing up a spherical balloon. The volume is increasing at 10 cubic centimeters per second. And we want to know how fast is the radius of the balloon changing when the radius is 6 centimeters. So typically when I'm dealing with a related rates question, the first thing I do sometimes is draw a picture. Drawing a picture here may be useful, maybe not. It's not like drawing the sphere is really going to tell us much more about the situation. You could. After that, if I've drawn a picture, the next thing I do is I like to think about what's changing. Specifically, what have they told me is changing in the problem, and what are they asking me to find how it's changing? So they've told me how what is changing. Volume. They've told me the rate of change of the volume. Great. So we know that volume is changing. And we're going to write down that the rate of change of the volume, dV dt, is equal to 10, and you can put units or not, cubic centimeters per second. What thing have they asked me to find how it's changing? I know it's hard to read. I know my writing is not great. It's the radius. So they've asked us how to find how the radius is changing. So they're asking us to find what dr dt is equal to. So my first step typically is to say, okay, they've told me how one thing is changing. I want to know how this other thing is changing. Cool. The second step is to find an equation relating those non-time variables. So find an equation, it's usually geometric, relating, in this case, volume and radius. Most of the time, this equation will be either the volume of your sphere, the volume of your cylinder, the area of your circle, the circumference of your circle, some either area, surface area, volume, circumference, or it could be a Pythagorean theorem kind of deal. But basically, the shape you've got, there should be some sort of equation we can write to relate the variables we're interested in. The goal is to use as few variables as possible. So we would highly prefer to write an equation involving just volume and radius and nothing else. That would be not possible if we had a cone instead. Right? If it was the volume of a cone instead of a sphere, the volume of a cone would be 1/3 pi r squared h, and then have like an extra thing you have to deal with later. But here we're totally set. The volume of a sphere is 4/3 pi r cubed. And that's probably something you're just expected to know, is these volume formulas. You can talk about more next time. It's like all the volume formulas you might need to know. Third thing, differentiate both sides with respect to time. Unless there's some other thing going on. I think there's one really nice problem where like your pressure and temperature change as you increase in altitude, and so you differentiate with respect to like your height and altitude instead of time. They're trying to like pick a different example of doing time, but most of the time it's time. So then the derivative of volume is dv dt, and the derivative of 4/3 pi r cubed is 4/3 pi times the derivative of r cubed is 3r squared times dr dt. Something cool I would like you all to see, just because it's super cool. What we really have up here or over there, what you really have is dv dt equals dv dr times dr dt. It's just the chain rule. You don't have to know that, but it's kind of nice to see that that is true. So sometimes people will do these really race things just because, oh, I want to find dv dt, but I want to do it in terms of r, so I know I'm going to have a dv dr and a dr dt. And you could think of the r's canceling, it's just that the dr is canceling. We're not going to cancel them, but you could think about them canceling and leaving you with a dv dt, which is kind of neat. Okay, so then after you've got your equation, and maybe we simplify it. I would probably simplify it because I'm a sucker for simplifying. It's going to be 4 pi r squared dr dt. After we simplify, then we plug in and solve. Sometimes plugging in and solving is more involved than others. Sometimes they'll give you everything you need. Sometimes you have to work a little bit harder to find some of the pieces you need. So if we're trying to solve for dr dt, that means we should be able to plug in for everything else. So we know that dv dt is 10, and we know that r is 6. So we've got everything we need. We have 10 equal to 4 times pi times 6 squared times dr dt. So dr dt is going to equal 10 divided by all that stuff. So 10 divided by 4 times 36 is 144, so 144 pi, which you could simplify as 5/72 pi. And then we should throw on some units. The units are always just going to be the units that make sense using whatever units they've already given you. Meaning our volume change was measured in centimeters cubed per second. Our radius was measured in centimeters. There's no like having to convert to some other thing. So I know that if I'm talking about how the radius is changing, it should be in centimeters per second. Because centimeters is my unit of length and seconds are my unit of time. You could also actually write in the units the whole way. And you can see here, right here, I would have, if you wanted, I would have centimeters cubed per second. And here I'd have 6 centimeters squared. And so then centimeters cubed divided by centimeters squared gives me centimeters per second, which is what I want. The units should always work out. If they're not working out, there's an issue. There's something else I want to say. Oh, something else not important at all. Just kind of cool, something worth knowing. The derivative of the volume of a sphere is 4 pi r squared, which is the surface area of a sphere. That doesn't work for other shapes. I want to make that actually super extra clear. It definitely does not work for other shapes. So for example, if you have a cube, the volume of the cube is x cubed. Hence the name. That's why we say that the third power is the cubic power, by the way. And the surface area of a cube is x squared plus x squared plus x squared 6 times, right? There's 6 sides to a cube. I didn't drop right the side back there. So the surface area is 6x squared, which is definitely not the derivative of x cubed. But there's this cool thing that, well, I don't know, cool. There's a really neat thing, which is true for circles and spheres, which is that if you take the derivative of their higher dimensional equation, you get their lower dimensional equation. So for a sphere, the volume of a sphere is definitely 4/3 pi r cubed. And the surface area of a sphere is definitely 4 pi r squared. And it also works for circles. What's the area of a circle? And the derivative of that is 2 pi r, which is the circumference of the circle. I don't know why that's true, but it is.